Wang Professor of Cognitive and Neural Systems at Boston University, as well as being the founding president of INNS and the general chair of the first of these meetings. And he has published over the last 50 years. His first known published work was in 1967, exactly 50 years ago, covering just about every area of mental function, and his work has accumulated a total of over 60,000 citations. And yet people are still surprised at some of the areas he gets into, and makes groundbreaking contributions, and now he's going to do that with consciousness. So, Steve.
Can you hear me in the back? Oh, good. So it's a great pleasure and honor for me to be able to speak to you today. And I'll be talking about an exciting and challenging problem towards solving the hard problem of consciousness, the varieties of brain resonances, and the conscious experiences that they support. In March, I published an open access article with the same title in Neural Networks, so anyone can read it for free if you're interested. It's also on my webpage. Well, what is the hard problem of consciousness? Wikipedia says it's the problem of explaining how and why we have qualia or phenomenal experiences. Chalmers has said the really hard problem of consciousness is the problem of experience. When we think and perceive, there's a whir of information processing, but there's also a subjective aspect. And then the Internet Encyclopedia of Philosophy goes on to say the hard problem of consciousness is the problem of explaining why any physical state is conscious rather than unconscious, is the problem of explaining why conscious mental states light up and directly appear to the subject. And we can still meaningfully ask the question, why is it conscious? So before jumping in, it's fair to ask, what kind of event occurs in the brain that's anything more than a whir of information processing? And what happens when conscious mental states light up and directly appear to a subject? Our brains sometimes go into a context-sensitive resonant state that can involve multiple brain regions. And in fact, I predicted many years ago that all conscious states are resonant states. But not all brain dynamics are resonant, so consciousness is not just a whir of information processing. Well, what is a resonant brain state? It's a dynamical state during which neuronal firings across a brain network are amplified and synchronized when they interact via reciprocal excitatory feedback signals during a matching process that occurs between bottom-up and top-down pathways. It's also fair to ask, how do different resonant states support different kinds of conscious qualia? And when does a resonant state fail to become conscious? Why and how do different combinations of brain regions support different kinds of conscious states, whether seeing, hearing, feeling, or knowing? My central claim is that conscious states are part of larger adaptive behavioral capabilities that help us to adapt to a changing world. We have resonances for conscious seeing that help to ensure effective reaching. Hearing help to ensure effective speaking, and feeling help to ensure effective goal-oriented action. So today I'll discuss properties of resonances that support visual, seeing, knowing, and reaching, auditory, hearing, knowing, and speaking, and emotional, feeling, knowing, and acting. And there's a burgeoning classification of resonances. I'll show you what I mean when I say surface-shroud resonances support conscious seeing of visual qualia. Featured category resonances support conscious recognition of visual objects and scenes. Stream shroud resonances support conscious hearing of auditory qualia. Spectral pitch and timbre resonances support conscious recognition of sources in auditory streams. Item list resonances support conscious recognition of speech and language. And finally, cognitive emotional resonances support conscious feelings and recognition of them. I should say this is a cautionary tale. If you don't understand a lot about how vision, audition, affect, and recognition actually work, and you can't say anything deep about how, when, and why their representations of individual experiences become conscious. So the talk will review aspects of this knowledge, but I want to emphasize that a huge amount more has been explained and predicted in over a half-century of systematic theory construction. I also want to make a disclaimer. I never tried to study consciousness. I just try to understand how psychological data emerge from individuals adapting autonomously in real time. But that always led to models of how brain mechanisms interact together to give rise to parametric properties of psychological data about conscious experiences. And here I'm talking about lots of psychological data, which created a linking hypothesis between brain and mind. These analyses led to the discovery of adaptive resonance theory, or ART, over 40 years ago. And many of you know that a unifying theme of ART is called the stability-plasticity dilemma, which asks how can learning continue in adulthood without causing catastrophic forgetting, or how can we learn quickly without being forced to forget just as quickly. And those of you who heard Alex Graves yesterday know that that was one of the first challenges he talked about for deep learning. And in fact, all the challenges he discussed have detailed proposed solutions within adaptive resonance theory. So ART's been incrementally developed ever since. And I think it's fair to say it's currently the most advanced cognitive and neural theory in the precise sense that it has the broadest explanatory and predictive range about how brains learn to attend, recognize, and predict objects and events in a changing world. And I'm glad to be able to say that all of the main ART predictions have been supported by both psychological and neurobiological data. Moreover, ART works. It's used in many large-scale applications in engineering and technology. A small number of them are on the CNS Tech Lab webpage, where you can see some of these, but there are many more. And the ART main idea is that top-down attentive feedback encodes learned expectations that dynamically stabilize learning and memory in an arbitrary world. In order to achieve this, object attention obeys what we call the ART matching rule, which says that attention is realized by a top-down, modulatory on-center, off-surround network. Well, what does that mean? Let's say I have bottom-up inputs trying to activate a field of feature detectors, other things being equal, it can do so. But let's say I have a learned category that's trying to read out its learned prototype to excite target cells. Well, it can't do it all by itself usually because it's balanced by an inhibitory off-surround. So this is a kind of one against one situation. But if the top-down prototype is active at cells getting bottom-up inputs, then it's 2 against 1, so these cells can have their activity selected, contrast enhanced, and indeed synchronized to start forming an attentional focus. Moreover, we know the laminar circuits where this happens. It comes from layer 6 in a higher cortical area to layer 6 in a lower one. It folds back to layer 4 and gives you a modulatory on-center, off-surround network. There's a lot of support for the ART matching rule. Attention does have an on-center, off-surround. This is a subset of experiments. It's been called biased competition by people like Bob Desimone and Leslie Ungerleider. Attention can facilitate matched bottom-up signals. Moreover, there's support for the predicted link between attention and learning for visual perceptual learning, auditory learning, and somatosensory learning. The predicted link between attention and synchrony has support, as does the link between consciousness and synchrony. Well, how does adaptive resonance get into the story? Well, attended feature clusters reactivate their bottom-up adaptive filters, then the activated categories reactivate their top-down expectations, and then you get an excitatory resonant loop that creates a feature category resonance that synchronizes, amplifies, and prolongs the system's response to the resonating cells. That's when resonance can trigger learning in both the bottom-up adaptive filters and the top-down expectations, and why I call it adaptive resonance theory. And by learning only within the attentional focus, outliers cannot cause catastrophic forgetting. So that's how feature category resonances get into supporting conscious recognition of visual objects and scenes. Attention will play a huge role in everything I say, whether it's object, spatial, or motivational. On the other hand, leading researchers like Christoph Koch have written that subjects can attend to a location for many seconds and yet fail to see one or more attributes. This happens in visual crowding, leading them to conclude attention isn't really important. But I'll explain these data using properties of surface-shroud resonances, which clarify how spatial attention is essential in determining what we consciously see. So we need to talk about how surface-shroud resonances support conscious seeing of visual qualia. But first I need to give you a little background. There have been many breakthroughs in brain computing and many more models that link detailed brain circuits to the adaptive behaviors that they control. And in so doing, new paradigms have been introduced, one of which I like to call complementary computing, which asks what's the nature of brain specialization. Well, in complementary computing, we find new principles of uncertainty and complementarity that clarify why you have multiple parallel processing streams with multiple processing stages in the brain, as illustrated by the famous macro circuit by Van Essen and his colleagues of the visual system. But what are complementary properties? First, let me comment their analogies like locks and keys fitting together or puzzle pieces fitting together. So let me say the following in words and then illustrate with increasingly precise examples. Computing one set of properties at a processing stage prevents that stage from computing a complementary set of properties. These complementary parallel processing streams are balanced against one another, a very yin-yang kind of situation, and it's the interactions between the streams that overcome their complementary weaknesses and support intelligent and creative behaviors. I say this with confidence because now we know quite a few pairs of complementary streams. These are just a few of them supported by theory and interdisciplinary data. And if we put several of them together, we get an emerging unified theory of visual intelligence from retina through prefrontal cortex, including the wide and where cortical streams, where many of these interactions, I would contend, are there to overcome complementary processing deficiencies of each of these processes acting alone. Well, let me mention two issues about vision to set the stage. So, and they're very much on the surface, that illustrates their profundity. When you move your eyes to look at the world, previously foveated objects shift to the periphery in a direction opposite to your eyes. Well, that shows that conscious visual percepts are computed in retinotopic coordinates. However, the perceptual stability that we experience as we scan the world depends on head-centered coordinates that are invariant under eye movements. Let me illustrate what I mean by talking about Euler stereograms. It can take tens or hundreds of milliseconds to binocularly fuse a Euler stereogram or a magic eye or a stereogram to be able to see what's hidden in these correlations. But after fusion occurs, if you move your eyes around, fusion is maintained. But if vision used only retinotopic coordinates, it should take just as long to refuse the image after each eye movement, and we lose perceptual stability. So we need to ask how and why do head-centered coordinates, which are invariant under eye movements, prevent this from happening? The second issue concerns figure ground separation. You look at this image, 3 rectangles abutting to each other, but they induce a compelling percept of a horizontal rectangle that's somehow in front of a partially occluded vertical rectangle. Well, how is the vertical rectangle completed behind the horizontal rectangle? After all, this is a 2D image. And why don't we see the occluded region through the occluder? Well, if we did, then all occluders would look transparent, because you could look through them all to stuff behind it, and that could cause great confusion in the development of reaching behaviors. I claim that a major design tension between seeing and recognition to prevent this from happening is resolved by interactions between cortical areas V2 and V4. So to get to these details, let me go back to some of these big predictions. Well, one was all conscious states or resonant states, which I know is confirming data. But a second one was all consciously visible qualia or surface percepts. Well, to understand what this means, we need to ask what's a surface? And here we need to discuss the complementarity of visual boundaries and visual surfaces. When we're trying to understand boundaries and surfaces, these are the regions in a macroscope, or macrocircuit going up to V4, pre-stride cortex. I like illustrating that boundaries and surfaces are complementary with the image of neon color spreading. How many of you seen it before? Well, it's always a good way to start. If you look at this, can you see this bluish color within the square? Can you? Okay. Well, actually, this is just built up out of these colored arcs. That's an illusion. And two things are going on here, boundary completion and surface filling in. The boundary that's being completed is a square boundary. It's completed in an oriented fashion, inwardly between pairs or greater numbers of inducers. It has to be between pairs or greater numbers of inducers, because if a single dot of contrast could create boundaries, they'd spread everywhere. You'd go nuts. On the other hand, the spread of this color is coming out of these places where the black and the blue come together for reasons I can't explain today, and that spreads in an unoriented fashion outwardly. So oriented, unoriented, inward, outwardly, you start to get the idea what I mean by complementarity. But what about insensitivity, direction, and contrast? Well, that's the difference between seeing versus knowing, or seeing versus recognizing. For example, with this Ehrenstein figure, they're just blue lines, but you can both see and recognize this circular disc because of the contrast difference between, which is an illusion. But in the offset grading, you can recognize that there's a salient vertical boundary here, but you don't really see it. Okay, it's not darker or lighter or a different color. So that shows that some boundaries are invisible or amodal. But actually, many years ago, I predicted that all boundaries are invisible, at least within the boundary stream. And one of several reasons is to recognize object boundaries in front of textured backgrounds. So if you look at the gray disk and you go around its perimeter, you have a gray-black that's light-dark, a gray-white that's dark-light, light-dark, dark-light, light-dark, dark-light. If you just build boundaries of the dark-light parts, you get a boundary with big holes in it. And if you both just build boundaries with the light-dark parts, you get another boundary with big holes, and a lot of color could spread through those holes, and everything would be a mess. To deal with that, the brain takes its oriented contrast detectors, simple cells at each position, you have them sensitive to dark light and light dark. They add complex cells which can now respond to both light dark and dark light. But by doing that, complex cells can't see the difference between light and dark. You've thrown away its ability to discriminate that qualia. So saying you're insensitive to direction of contrast by pooling over opposite contrast polarities shows that all boundaries are invisible. Well, if boundaries are invisible, how do we see? Well, this is accomplished by filling in of surface color, in which boundaries define the compartments within which lightness and color spread, whether in the Ehrenstein or the neon case or whatever. The Craig-O'Brien-Korn suite effect is a beautiful illustration of this. How many of you know that? Well, if you enter vision and you want to understand human vision, you got to think about these issues because they totally change the design issues that you tried to solve. Well, this looks trivial. Uniform dark gray, uniform light gray, black border. I'm going to remove the black border and pay close attention because something interesting is going to happen. Ready? Go. So the point is that really both sides here have the same luminance. And if you remove the black border, you can see this less luminous cusp and more luminous cusp. But when you put the border back, you can't fill in around the cusp anymore. And so the less luminous part gets trapped in here and fills in. The more luminous part gets trapped in there and fills in, making it look uniformly gray of a darker or lighter variety. So boundary completion defines filling in compartments, and filling in determines what we see in each compartment. So when we're sensitive direction of contrast, that means we are filling in visible color and lightness as a surface percept, leading the innate 84 to predict that all boundaries are invisible in the interblock cortical stream, and all visible qualia are surface percepts in the blob cortical stream. So now I can talk about all conscious states or resonant states. All consciously visible qualia are surface percepts. But if you put them together, you're forced to ask what type of resonance supports conscious percepts of visible qualia. That is to say, how do we see? And that drove me crazy for a long time, until in 2009 I could predict that that's accomplished by surface-shroud resonance. Well, then we need to ask, what's a surface-shroud resonance? And to fully answer this question, we need to study invariant object learning and recognition. Very hard problem, which is why it took so long. So here we need to ask some very basic questions. What is an object? How does the brain learn what an object is under both unsupervised and supervised conditions? Moreover, how does the brain intelligently scan a scene with eye movements, like in this famous scan published by Arbus of what eye movements look like when you're looking at Nefertiti? Why don't the eyes just jump around randomly? And if you put them together, you need to ask, how does the brain learn to bind multiple views of an object into a view invariant object category while it's scanning its salient parts with eye movements? That's all about active vision. So here we need to look at spatial attention, and here we need to look at spatial attention and tracking, and here we need to look at spatially invariant object recognition higher up in the what and where cortical streams. So a key issue is that during unsupervised scanning and learning about the world, no one tells the brain what views belong to which objects while it's learning view invariant object categories. So if you're scanning these three different pairs and you put it through the log polar cortical magnification factor between the retina and cortical area V1, that's what you'd see. Really hard to know if you moved off a pair. But the brain must somehow be able to learn multiple views of an object when the eyes move on the same surface, and then somehow know how to stop learning when the eyes move off that surface. And I claim that this is achieved in the following way. Let me just say it in words and then I'll give it teeth. So a pre-attentively formed surface representation, for example in V4, activates what's called an attentional shroud in the spatial attention region, such as posterior parietal cortex. An active shroud is going to inhibit reset of an emerging view invariant object category as it's being associated with multiple learned view-specific categories of the surface that are being reset as the eyes move. So let me say it again. You're looking at multiple views of the teapot. A small set of views can be quickly categorized into a view-specific object, a view-specific category. Let's say an infratemporal cortex, the posterior part, ITP. And then when activated, these cells are going to activate some cells up here, which is in the anterior part of IT. But when the view changes enough, you want the view-specific category to shut down so you can learn about a new view-specific category that you want to associate with the teapot, and then another view-specific category that you want to associate with the teapot, thereby making it view invariant. But when you shut off the first one, you also shut down the input that turned these cells on in the first place. So how do they stay on to be able to be associated with all these things? The claim is that an attentional shroud does that. Well, what is an attentional shroud? It's been known for a long time that spatial attention fits surfaces. And Tyler and Kontsevich called this an attentional shroud. Many people studied form-fitting spatial attention, but I predicted that shrouds do more than that. They enable learning of view invariant object categories, and I want to explain how. So first, how do you form a shroud? Well, let's say you're looking at a cross-sectional cut through a very simple picture where this bar is a little more luminous than that. So this surface is going to bid, sending excitatory signals for spatial attention. This will be a little more active than that. There's going to be a lot of competition. But there will also be top-down excitatory feedback, turning this into a recurrent, contrast-enhancing on-center off-surround network, forming a form-fitting shroud over the surface via a surface-shroud resonance. And in so doing, it increases the effective contrast of an intended surface, as has been verified psychophysically and neurophysiologically. So an active surface shroud resonance means that sustained spatial attention is focused on the object surface. And we try to understand how this works in the ART-SCAN model by looking at interactions between a lot of brain. Today I just want to emphasize a couple of key points. Namely, an active shroud maintains activity of the view invariant object category as the eyes move as follows. Let's say you have a surface shroud resonance. Your eyes are moving around, learning view-specific categories that are associated with this emerging invariant object category. And this isn't being shut down because while the shroud is active, it's inhibiting parietal reset cells that would have shut it off. But if spatial attention shifts, okay, you're going to remove that inhibition. You'll get a burst of activation in the reset cells that'll shut these guys off, and now you could pay attention to a new object and learn about it. Why should you believe that? Well, just as we were publishing that, Steve Yantis' lab in the Journal of Neuroscience had a beautiful paper using rapid event-related fMRI in humans, and these are their words. Spatial attention shift, that means shroud shuts down, causes domain-independent transient parietal signal, that means category reset burst, which causes a shift in categorization rules, meaning you shut off this category so you can learn another. Why is this domain independent? Because any object can inhibit this, and this can inhibit any invariant category. Well, now let's look at how do we know where to look next. In particular, why don't our eyes jump around randomly? How does the brain know how to scan salient features of objects? Moreover, how do scanning movements occur within an object, even before an object category is defined, so that we can actually learn invariant categories? Random eye movements don't support learning invariants. Well, I think whatever else you'd believe, you'd agree that movement targets during directed search are chosen after the brain stage where surfaces get separated from each other via figure ground separation. Because if they haven't been separated yet, they're just one big blob and you can't really focus on one object versus another. So you gotta know something about figure ground separation. Well, I was forced into thinking about that because boundaries and surfaces are complementary. And so you need to ask, how do you get out of complementary mechanisms one consistent percept of an object? And I showed all the way back in '94 that feedback between the V2 boundary and surface streams gives consistency, and then remarkably, it also initiates figure ground separation. So the intuition here is that you're in V2, boundaries are gating the filling in of object surfaces, but in addition, the filled in regions and object surfaces are sending what's called surface contour signals back to the boundaries to strengthen the boundaries that succeeded in generating closed boundaries in the surface region and inhibiting all the other spurious boundaries, and that enabled figure ground separation for reasons I can't tell you today. But how do you get the surface contours? Well, I should first say, why should you believe this? It's so vague. Well, the theory has explained all of the V2 cell neurophysiological data about figure ground properties from Rudiger van der Eyck's lab in a paper I published this year. In fact, I predicted most of those properties, but not all. So when you're forming a surface contour, you have a filled-in surface, and you have a contrast-sensitive on-center off-surround net that is just going to respond at the bounding contours of the surface, and that's how it's going to strengthen the good boundaries while it's killing the bad boundaries. But because this is an on-center off-surround net, where you have high curvature points, the surface contour is more active. So it's more active at salient features, and by picking the features in order of their size, you can get a target position that is going to tell you how you're going to be able to search this object. And so the idea is that these target positions are going to be generating eye movements within the object as the shroud stays active, as has been supported psychophysically. They're going to determine where attention shifts, as has been supported psychophysically. So that we're starting in this circuit to unify spatial and object attention, figure ground separation, eye movements, and visual search. But where is this going on, this transition from vision to action? I believe it's going on in V3A. There's data about that. And here's a quote from a beautiful paper of Kaplowitz and C. Neurons within V3A process continuously moving contour curvature as a trackable feature. That's what I'm trying to explain to you today. But in addition, this target position isn't just generating an eye movement that takes a while to occur. It's rapidly updating a gain field that's going to transform a retinotopically computed surface into a head-centered shroud, which is invariant under eye movement, so it can maintain the inhibition of category reset, so you can learn the invariant categories. This is called predictive remapping, and this circuit also clarifies predictive remapping. So there are several functions of a surface shroud resonance. It sustains spatial attention on an object of interest. It prevents reset of an invariant object category while controlling how the eyes look at the object's different surface features. It uses predictive remapping by gain fields to maintain the shroud and head-centered or spatial coordinates that are invariant under eye movement so that the shroud can prevent reset as eye movements explore the surface, which itself is computed in retinotopic coordinates. And finally, it supports conscious awareness of the object's surface qualia. Well, why is surface shroud resonance generated between V4 and PPC? The claim is that V4 generates a sufficiently complete and stable visual representation upon which looking and reaching movements can be based. Then these resonating signals propagate top-down to V1 and V2 and bottom up to the prefrontal cortex using the arc matching rule to select consistent information and to suppress inconsistent information, so that only information that can support effective decisions and actions remains. In particular, it happens in V4 after the visual brain resolves 3 hierarchical resolutions of uncertainty due to complementary computing. The first concerns the fact that hypercomplex cells complete boundaries at line ends. We know you have oriented simple cells, but they can't see high curvature points or the ends of lines. There's no boundary here, so color would flow out of every line end. The hypercomplex cells, the simple, complex, hypercomplex, or end-stop hypercomplex cell circuit builds boundaries here called end cuts and prevents that disaster. The bipole cells that do perceptual grouping convert fuzzy initial groupings into final sharp groupings. They need to be fuzzy initially or they never start to form. Bipole cells have been confirmed physiologically, psychophysically, and everyone uses a version of them to model. And then filling in cells in V2 and V4 complete surface representations using feature contour signals that discount the illuminant. So before filling in, you'll have a boundary contour, an illuminant discounted feature contour, then it'll fill in just like in Quaker-Grindcorn Suite. This has to happen before you have a good enough representation on which to base movement. And in fact, neon color spreading can be explained by these 3 processes interacting together. But in addition, we need to understand that V4 completes 3D figure ground separation of the unoccluded parts of opaque surfaces. And these surfaces are what we consciously see. In particular, V2 and V4 resolve a basic design tension between recognition and seeing. How do we recognize a partially occluded object, but we don't see the partially occluded part when the occlude is opaque? If we did all occluding objects would look transparent, and you'd have problems deciding how to reach and navigate because you'd be reaching through stuff. I claim that seeing adds an extra degree of freedom that prevents this problem. So we see to reach in part. So V2 completes partially occluded 3D boundaries and surfaces for amodal recognition, but V4 completes the figure ground separation of 3D boundaries and surfaces of unoccluded surface regions for both conscious seeing and recognition and effective looking and reaching. So with surface shroud resonance between V4 and PPC triggers visual consciousness as an extra degree of freedom, whereby the V4 representation can be used to plan looking and reaching movements to unoccluded surface regions. But why should you believe it? It explains a ton of data about multiple visual phenomena. The models have simulated a ton of data over decades. And there's a lot of physiological data about V2 and V4 compatible with this, but of course we need more experiments. Well, now let me explain some clinical data about consciousness with surface shroud resonances to illustrate the range here. I'll look at parietal visual neglect. If part of your parietal cortex is missing and you're drawing the world, you won't draw that part of the world. You might not put clothes on that part of your body. So a part of it's trivial. If you knock out part of parietal cortex, even though the visual system's good, you can't get a surface shroud resonance, so you're not conscious, QED. Not so fast, because it's a very complicated area. And Driver and Mattingly have a classical review of effects of lesions in inferior parietal lobule, or IPL, that we can now better understand. So, the head-centered shroud coexists with retinotopic surface qualia. That's shown by how neglect varies with the patient's direction of gaze. Competition for spatial attention across parietal cortex is shown by how neglect varies with isolated versus simultaneous cues. Preserved figure ground segmentation during neglect is shown by how grouping can overcome neglect. Unconscious processing of neglected object identity, the difference between seeing versus knowing, is shown by implicit knowledge of neglected stimuli. So we need to look at the difference between seeing via a surface shroud resonance into the WAIR stream and knowing via a feature category resonance into the WAT stream. They are linked together in pre-stride cortex synchronously so that we can know what the object is as we see it. There's a link between visual neglect and motor planning deficits. This is the seeing to reach issue shown by abnormal motor biases. Moreover, IPL lesions lead to deficits in sustained visual attention because there's no surface shroud resonance to maintain attention. Moreover, if you make a lesion in the WAT stream, you get visual agnosia, reaching without knowing, as shown by the famous patient DF of Melchadol et al. You can explain a lot of other stuff. I'll just make a comment about visual crowding, because that's about Christoph's claim here. In visual crowding, let's say I can see the letter T surrounded by these letters T. If I move toward the periphery and I expand all the dimensions, I can still do it because of the cortical magnification factor. But if I don't, then all of them can be surrounded by one shroud. If you don't have your own shroud, you can't be seen or recognized as a separate event. So now you can say a ton more about vision, but I got to go to audition. And there are Watt and Warehouse streams in audition as well, ventral and dorsal streams. In fact, in a famous paper of Hickok and Propel, they talk about a ventral sound to meaning and a dorsal sound to action. Well, if you're going from seeing and reaching to hearing and speaking, you need to consider the circular reactions of Piaget. But what's a circular reaction? A baby can endogenously babble arm movements. Its eyes can reactively track its moving hand. It's learning associations from hand position to eye position and conversely. So later in life, it can volitionally reach where its eyes are looking. You need to do this to get any decent robot. Well, we introduced the direct model, we being Dan Bullock and our student at the time, Frank Gunther. It learns by a circular reaction. You have an endogenous random generator that generates babbled arm movements. It also learns a spatial representation to mediate between vision and action, because if you do that right, you get motor equivalent reaching. You can reach a target with clamped joints, but also quite wonderfully, we discovered, you can also reach a target with a tool on the first try under visual guidance. That's like putting a virtual joint on the arm. And so if you ask how did tool use arise, I would claim if you know how to learn a circular reaction right. And here you have some simulations, an unconstrained reach, an elbow clamp by 140 degrees, motor equivalence, and here's an accurate reach on the first try with a tool. So we need to ask, why are there homologous circuits for development and learning of motor equivalent reaching and speaking? Because when Frank got his PhD, he introduced the DIVA model for speech production, which has become the leading model in the world, and it's homologous to the direct model. And here, co-articulation occurs where tool use occurred here. Well, why should there be a homology between reaching and speaking? I believe it's true, and in fact, we discussed it with Frank while we were still working on direct, that reaching and chewing during eating are a coordinated sensory motor system that has similar dynamics, and speech evolved from articulates for eating. And if only for this reason, we find similar data about auditory neglect as visual neglect due to IPL lesions, including impaired auditory spatial perception, impaired sustained attention, and impaired speech production. And that's why there is stream shroud resonances that support conscious hearing of auditory qualia, much as surface shroud resonances do a similar thing in vision because of that deep homology. Well, what does art have to do with it? Well, art in the temporal domain enables auditory speech and language representations to be rapidly learned and stably remembered. Let me first briefly mention spectral pitch and timbre resonances that support conscious recognition of sources in auditory streams. Well, auditory streams are all about the cocktail party problem. How do you separate multiple acoustic sources so that you can recognize them? And I believe that streaming plays a role in audition similar to the role played by figure ground separation in vision. And a very nice example of this is the auditory continuity illusion. There are three stimuli. In one stimulus, you have a pure tone followed by broadband noise, followed by the same pure tone. In the other, you just have tone noise, and the other, you just have tone, silence, tone. And if you do the noise right, you'll hear the tone going right through the noise here, but it doesn't happen here or here. And what's really interesting here, these two stimuli are the same till the second tone occurs. So the critical question is, how do things go backwards in time? How does a future sound let a past sound continue through the noise, but it won't happen if there's no future sound? And the answer is resonance takes a while to kick in, but after it starts, a future tone can maintain it much more quickly. And why doesn't it happen if there's no noise? Well, that's the art matching rule. It's modulatory. You need bottom-up input. And we've modeled this in what's called the art stream model, which claims that a stream is a spectral pitch resonance. This didn't get to timbre yet. But what about item list resonances that support conscious recognition of speech and language? Well, here at a higher level of the auditory system, in the case of language, you have a phenomenon called phonemic restoration. How many of you know what that is? Well, again, this is critical data if you want to understand how humans do speech and language. If you don't care, it doesn't matter. But it has to do with what are the functional units of speech and language and how are they computed. So let's say you just have two words, delivery and deliberation. They both start with this deli. Replace the V and the B by broadband noise. If you do it, you'll hear delivery and deliberation perfectly well. But if you put in silence, then you won't. This is again the art matching rule on the level of speech and language. And the conscious art word model is a laminar cortical model that has simulated how this happens, how future context can disambiguate past data, and still you have a conscious person from past to future. I mean, there's a very big breakthrough conceptually in understanding how speech can be disambiguated in noisy situations using past and future context. And here we show how conscious speech is a feature itemless resonant wave. Well, finally, I want to tell you a little bit about cognitive emotional resonances. I'm sorry to be, sort of dragging you along on this big wave, but I want to at least interest you enough in the topic to realize that we really know what we're talking about here. It's not a complete theory, but there's too much evidence not to follow up with it. So cognitive emotional resonances support conscious feelings and recognition of them. And here it's important to realize there's a link between conditioning and consciousness, and that the hippocampus plays a major role in bridging temporal gaps, while also being crucial for memory consolidation. I don't know how many of you know enough about the cognitive neuroscience literature to have heard about the famous amnesian patient, HM. So some of you have heard of HM. He's become quite famous. He had bilateral hippocampectomy. It's also been shown in studies that amnesics with hippocampal damage can do delay conditioning, but not trace conditioning. And Larry Squire, who's a leader in the field, has noted that trace conditioning requires the acquisition and retention of conscious knowledge and requires the hippocampus. Well, what are delay and trace conditioning? In delay conditioning, I might have a conditioned stimulus like a bell and an unconditioned stimulus like a shock, and they overlap in time. In trace conditioning, there's a gap between them, and you got to somehow bridge that gap. Just this year, in another open access paper with my student Dan Franklin, it's open access and on my webpage, we attacked the question of memory consolidation, which is why do lesions of thalamus, amygdala, hippocampus, and orbitofrontal cortex have dramatically different effects when they occur in different phases of learning? I won't go into this, but I'm telling you this because you can explain all those data if you understand three very basic competencies that we all know we have. One, we pay attention quickly to salient events, both positive and negative, and that uses our amygdala. But if you did have a rapid attention shift to focus on a salient event, it could cause premature responding that could get you into bad trouble. So that's not enough. But that problem's eliminated by the second and third competences. The second is, how do you adaptively time and maintain motivated attention on a salient event until the response is executed? This needs the hippocampus. But in addition, how do you adaptively time and execute an appropriate response? And that needs the cerebellum. So I believe classical conditioning has been used a lot to illustrate this because it's adaptively timed. In it, you'll have a CS that's a neutral tonal light. The US is a puff of air to the eye or a shock to the orbital muscle. And the conditioned response, what's learned, is an adaptively timed nictitating membrane reflex or eyelid closure, nictitating membrane in a rabbit, an eyelid in human. And here's some beautiful data. Let's say that's your ISI, that's the probability of response. Let's say that's your ISI, that's the probability of response. So notice the ISI co-varies with the variance of responding. That's called a Weber law. And if you have two ISIs, you have your own little personal Weber laws there. So how does this work? Well, pay attention quickly to salient events, both positive and negative. How does that work? Well, many years ago, I introduced the cognitive motion motor, or COGM model, which talks about how invariant object categories, we just discussed, activate sensory cortex, that there are value categories in the amygdala and hypothalamus, and then there are object value categories in the orbitofrontal cortex. And so what's going on is this: a conditioned stimulus tries to activate its object category. You could have learning by pairing a CS with a US until the stimulus can activate the amygdala and all of these feelings using conditioned reinforced learning. That kind of conditioning can also learn instead of motivational learning, which can try to activate the orbitofrontal cortex. And it requires a sensory cortical input and this amygdala pathway in order to fire orbitofrontal cortex, for which there's a great deal of data known. In fact, there's a famous anatomical diagram from Helen Barbas, one of the best anatomists in the world, showing all the sensory cortices going directly to amygdala and to orbitofrontal cortex, and amygdala going here, and the theory anticipates this by 20 years. But you need more, because motivated attention needs to close the cognitive emotional feedback loop to focus on relevant cues while competitively blocking irrelevant cues. And in fact, this is the basis of core consciousness and the feeling of what happens. If you read Antonio Damasio's beautiful book of that name, he derives the heuristic version of this very circuit from his clinical data. But the question is, how is the resonance maintained long enough to become conscious? And the answer, I believe, is that the hippocampus, can sustain an adaptively timed cognitive emotional resonance that can support the feeling of what happens and knowing what event caused that feeling. So we need hippocampus as well as amygdala. So how does this stuff work? Well, rewards and other goal objects are often delayed in time subsequent to the actions or events that elicit them in any terrestrial animal or robot. And so the question is, how do humans and other animals learn to wait for a reward? Well, if you wait too little and just restlessly explore, you'll never get fed and you'll die. But if you wait much too long and the food doesn't show up, you might starve to death and die. So this is a question of balance in exploratory and consummatory behavior. You need to excite exploratory behavior to search for new rewards. But you also need to inhibit it when you focus attention on expected rewards in order to consummate. So here we need to distinguish expected versus unexpected non-occurrences of goal objects. An unexpected non-occurrence is a predicted failure. The reward that doesn't occur when you expect it. And here there are lots of orienting reactions. You shift your attention, you get pissed off, you try to get the hell out of there to explore. But what if it's an expected non-occurrence? You have a predictive signal, a while later there's an expected goal, and then there's all this other stuff that happens in between that can distract you. And if it did, you'll never get the goal. So this leads us to look at expected non-occurrences, noting that some rewards are reliable but delayed in time, and you don't want oriented reactions there. So how is that ensured? Well, both the expected and unexpected non-occurrences are due to mismatch of a sensory event with a learned expectation. But the expected non-occurrence don't inhibit sensory matching, because if a pigeon saw food earlier than expected, he'd eat it quite happily. I predict that expected non-occurrences inhibit the process whereby a sensory mismatch would have activated the orienting system. You just don't let it happen. And this shows a beautiful homologue between recognition learning and reinforcement learning. In the attentional system, you have interaction of the orienting system, but in the reinforcement learning system, the cortex is going to go to the drive representation and give you adaptively timed inhibition of orienting, so you don't get the orienting response. And this is achieved if you can solve a timing paradox. In particular, let's say the CS occurs and the US occurs a while later. Well, you want your timing to be accurate. You want the response to be well-timed. But you also want to inhibit exploratory activity throughout that interval. So you want to be fuzzy and you want it to be sharp. How can you have it both ways? Well, if the response gets activated immediately and peaks at the ISI, then you'll have inhibition of orienting for all time, but you'll also have a peak response when the reward is expected. And now if you vary the ISI, what do you get? You get the Weber law. The Weber law solves the timing paradox. And in fact, the Stark model explained how this happened by showing how the adaptively timed hippocampal circuit could maintain inhibition of the orienting system as it gave you adaptively time motivated attention that peaked at the ISI to cause the response. Well, how is this done? I predict it's done by spectral timing. We started publishing this in '89. There was also beautiful psychological work, classical physiological data, and more recent physiological data, in fact, at BU on so-called time cells. How does it work? This is the simplest example. An input comes in, a CS. It's stored in short-term memory for a while. It activates a spectrum of cell sites that respond at different rates. These activities are gated by a habituative transmitter. So if an input comes in and it interacts with the transmitter, that's what happens to the transmitter when it habituates. But the output is the product, which has an overshoot before it's levels off. Now, if you have a whole spectrum of activations, then these habituating gates will shut down at different rates, and you're going to have different intervals of sampling. And if they're sampling in an adaptive way that's looking at the US, and you add them all up, then you get beautiful adaptive time, and you get the Weber law automatically, and the double peak. So now in the next minute, I want to comment, why aren't procedural memories conscious? And the reason is their matching and learning laws are not resonant. So if you have an art match, you get excitatory matching and match-based learning. But if you're doing movement control, you have a target position command, a present position command of where you are now, which you subtract from the target position command to give you a difference vector that's integrated until you are where you want to go. The difference vector is 0, match is suppressive, and learning here uses the difference vector, so you have mismatched learning. So here you can't be conscious. You don't have resonance. So the what and where streams are complementary. In the what stream, you have spatially invariant object learning and recognition, and fast learning without catastrophic forgetting. In the where stream, you have spatially variant reaching and movement, where you continually update sensory motor maps and gains. Neither is sufficient alone, but perceptual and cognitive processes use art-like excitatory matching and match-based learning to create self-stabilizing, attentive, and conscious representations of objects and events that embody increasing expertise about the world. Complementary spatial and motor processes use inhibitory matching and mismatch-based learning to continually update spatial and motor representations to compensate for bodily changes throughout life. Together, they provide a self-stabilizing perceptual and cognitive front end for conscious awareness and knowledge acquisition, which can intelligently manipulate our more labile spatial and motor processes that enable our changing bodies to act effectively on a changing world. Thank you very much for your sustained attention.
I'd just like to mention that I was initially skeptical about the idea of that all conscious events are resonant, because
when we're trying to make sense out of a new object, there's a period of time that we haven't classified yet, and yet we're still conscious of that. So is what you're saying that we're resonant on the lower visual level before we get resonant on the higher knowing level?
No, it's not a lower level. It's the difference between seeing and knowing.
Yeah, that's
Seeing
what I
is
meant.
general purpose. You can see things whether you know them or not. Knowing requires the learning of feature category resonances. But seeing is general purpose, knowing is not. So that's why, and it's very confusing, so that's why you have this surface-shroud resonance, which is mediated through aware stream. At the same time, you have feature category resonances mediated through the Watt stream, interacting in prescribed visual cortex. And it took me, as I say, many years to begin to understand that. But then when you just say, hey, just knock out the feature category one, and you can explain hard data about visual agnosia, things that people write whole books about now can be explained in a few minutes. Likewise with all this stuff about parietal neglect. Who can touch it without a theory like this?
Thank you very much, Steve. Every time I hear you, I learn more, and it's fantastic the work you have done. Can I ask you a kind of funny question? My son is just finishing high school and is learning for his exams, and he's going to coffee shops because he can concentrate there much more. So there seems to be this background noise. So the flow of thought seems also to be guided by the type of resonance. Could you explain it this way? Or?
Well, if you, I know I moved pretty fast today. Remember I said that when you get a surface-shroud resonance, and not only a surface-shroud resonance, what I'm talking about is the generator, the trigger. But then stuff propagates top-down and bottom-up, where the art matching rule is trying to suppress irrelevant stuff. Now, to the extent to which other stuff can break through, it will distract you. So in particular, if I had more time, I would explain better how spatial attention is controlled both by these surface-shroud resonance kind of things, but also you have transients that are coming in from the motion system that can rapidly distract. And it's a tug of war between these slower developing surface-shroud resonances and the transients, which are going both to parietal and prefrontal cortex. And those are crucial to, for example, if you're doing social cognition and a teacher moves her arm, the transients are going to be a kind of guide to a flowing surface-shroud resonance to the arm. So yes, the art matching rule tries to knock out distractors. There's a lot of shit going on, and in particular the motion system can try to break in. And one of the issues is how does motivated attention give you kind of cost function against how much distraction will be tolerated before a new challenge will be allowed to grab your attention. So it could all be formulated in very, very much in an applications engineering setting.
Steve, thank you for the talk, and I've been getting support from you for the community, and also including Plenary Institute. Appreciate it. But I put in a more direct way, because we can talk about it privately, but I put a more direct way so the message is passed on, all right? I do not
The message
really
is
mean,
what?
no, I put more directly the question.
Wait, what is the message? I didn't hear.
The man, I have not started yet. I just say that my message is direct, so that I do not mean to be offensive, and I do not mean disrespect, so that the message can be passed more directly. Do you understand? I have not started my message yet, all right?
Well, then stop being ad hominem.
So originally, I did not plan to come, because I have listened to your talk many times, including early on at ICDL.
I haven't given this talk many times.
No, the next I see there are new material, right? You have new material. But my message was that I still come, all right? Because I think that I like to the new material you are doing, and also like to ask questions that could be useful to you and others, all right? I think that we understand our brain. Brain builds itself. It's not like a car. If you look at
I can't understand.
a car is different from a brain. Car is very complex. You say, I can know this engine, there's a muffler, it does what, and there's oils that burns, all those things.
Could
And
you
you-
ask me a question relevant to
No, I can relate to the question, before the question. So my question was that, how do you deal with a brain that builds itself through lifetime, from preconception to baby time, to postnatal time, it builds itself. And your work focuses on how the car is. A lot of you say, seeing and knowing. Where does seeing and knowing come from?
Wait a second.
Now let me finish your question.
No, I want to respond right away. Art is all about learning throughout life. That's the stability plasticity dilemma. There are also many studies that have been published over a period of decades that show how the laws for development are continued in a self-consistent way into adulthood. So you're really bringing up
You
a-
said Jean Piaget.
This is
You know
wrong,
that. But
John.
Jean Piaget was saying that how baby act, the need and act that contributed to the understanding of knowing.
Why
And
do you think I mentioned the circular reaction?
Yeah, you mentioned it, but you did not
No,
explain.
we've modeled them, John.
You did not explain the causality of
I
real
can't
what
explain
network.
4
No, I want to
years
finish.
of detailed
I want to
research.
finish. I do not mean to distract. okay?
John, colleagues, I wanted to interest
I
you
get my message
in
passed.
some of the issues.
John,
If you want to look into them more, please do. I'm Steve at BU. I love talking. His comments are irrelevant to my talk. Thank you.
I had a question about, I'll try to make it very brief, a two-part question. One is about the phenomenon of flow, because it seems like when we get, we build up to this level of attention, and then we get to an exquisite level of hyper-attention, where we no longer seem to at least affectively experience consciousness anymore. It's as if we go below consciousness, through consciousness, and beyond consciousness. So that's part one. And part two is about the processing speed. So with these...
Could I do part one first?
Sure.
First,
Well, I'll just...
I don't want to forget.
Yeah, but the other part is just about how can our human neurons that process in milliseconds do these cycles. So I'll step off, but anyway, I just wanted to be brief.
Okay, well, both questions are deep and important questions. Part of the first question is not to be viewed just in terms of the conscious experience. It has to do with the kind of chunking during learning. And when you have very, very big chunks, they can automate a lot of the things you do so that you can spend more attention on other tasks. Just like when you're driving and you're thinking about something or listening to music. So the whole issue of chunking is huge. In fact, Alex Graves mentioned chunking in a vivid way in his talk, and there's a highly developed theory of how working memories and chunks, how working memories are designed, how chunks are learned, and it's supported by psychophysical and direct neurophysiological data. But I think it's all about the issue of chunking and how that enables attention to be allocated in a more distributed way. As to the timing, one of the early results that Gail Carpenter and I showed, well, you know, for example, Alex also talked about how long you process, okay? And in laminar cortical models, they run as fast as they can given the amount of uncertainty in the data. So when you have familiar data, you can shoot through in a feed-forward pass. And in fact, there are good cognitive data One of my friends' names is escaping me at the moment, but there's good cognitive data about very fast recognition even of a complex scene. On the other hand, the Lamina models are designed with self-normalizing in excitatory and inhibitory interactions. So if you have multiple choices, each of them gets less activity that automatically slows down processing. Then internal feedback loops, contrast enhance the most certain data, drawing activity into them and then speeding the processing. So it automatically runs as fast as it can, slows down to contrast enhance the data to get to the best decision it can, given the uncertainty of data, and then speeds up again. It's like what Bayesian people are trying to do, but this happens in real time, and it's compatible with self-organized learning, and it's supported by the gorgeous circuits that are in our cerebral cortex.
Great, thanks.
Very interesting talk. I wanted to ask, when does the resonance stop? Are there different levels of consciousness, like one that will take longer
Could you
or
talk
stronger?
louder, Heather?
Oh yeah, I'm sorry. It's my regular problem. Is it better now?
That's good.
Okay, so are there different levels of consciousness? Is there different levels of resonance that will take more time or be faster or slower, or different characteristics?
Well, here I just talked about these 6 kinds. They can also link together. For example, when I talked about the cognitive emotional work, where invariant object category can link to that circuit so that you can have this kind of feature category resonance synchronizing with a cognitive emotional resonance and synchronizing with a surface shroud or stream shroud resonance, depending on what the data are. So this all will happen in a coordinated way through time. What I thought you were going to ask me was, when a positive feedback loop like resonance starts, how does it ever stop? And all of these excitatory feedback loops have activity-dependent habituative gates. So the thing will collapse under its own weight after a while, and more as other bids come in that haven't been currently active, they will win for the competitive struggle. So that's part of what happens in addition to mechanisms of inhibition of return. So activity-dependent habituative gating and feedback loops combined with inhibition of return help to explain a lot of shifts.
Thank you.
Okay, time for one more.
You go.
Hey, so I guess from the the computer science perspective, the thing we're always trying to do is create more accurate classifiers for information, right? So if you see the scene, you can say that resonance under this model is sort of a mechanism to combine different classifiers to create a more accurate representation of data. But I'm curious, what?
I wouldn't say that's correct.
Okay.
In particular, here I talk about the dynamics of resonance, but Dale Carpenter and I in particular have put a lot of effort into developing machine learning algorithms that embody our feedback. They called ART1, ART2, ART3A, ART2A, ART3, fuzzy ART map. And they're used in all those art applications I've flashed on. So the feedback in the resonant model is there for you to be able to learn quickly without forgetting stuff you already learned, which is a problem that deep learning has that Alex mentioned. That stability plasticity problem is solved in art. But now ask me a question. It's just you were saying something that wasn't quite accurate.
Okay. So I guess I'm a little unclear on the link between consciousness and this hypervisor process that just sort of reconciles data.
I don't know what that means. Could you say it in a different way?
Yeah, so we've got this resonance model, and the resonance model, as I understood it at least, is just sort of this this feedback system that is preventing like context switching, and then the end result of that is that we're like able to do this learning process. But how is that how is that consciousness instead of just a way to achieve better categorization of information? Or is that all that consciousness is?
Well, okay, well, first, from the computer science point of view, if you haven't looked at it, there's a paper that I published in 1987 with Joe Carpenter, the simplest version of an art algorithm. It does winner-take-all categorization, and it's only dealing with binary vectors of arbitrary dimension and arbitrary order. And it proves theorems, so you don't have to wonder how it's working with theorems. But what I was trying to clarify here, but I went fast, is that, like in vision, why do we become conscious? I try to point out that consciousness gives you an extra degree of freedom whereby you can use the figure ground separated V4 representation of surfaces to control a looking movement or a reaching movement. Without that, there would be data everywhere. You wouldn't know what stage should give you the information that you need to make the movement decision. And why it was in V4, why I predicted it's V4, I sketched, but part of it could be wrong. There's a lot of evidence for it, but these are a number of new ideas, and I hope people really grind at them and find if they're errors. But it gives you a representation of the data that can be used by the appropriate action in that modality. That's why when I was talking about reaching and speech production, the same thing is true in speech production, I would claim. But I had to do it with such a sleight of hand to spend like 5 minutes on it, that it could easily have gone by. But that's the answer I've come to, that we're not here to just platonically contemplate the world. We need to be able to make decisions and actions. And the conscious representation, when it resonates, says, these are good enough data on which to base that action. And until that point, it's not ready. But the resonance will occur as soon as the representation settles down, after it goes through all of these things I sketched. Okay. And once the resonance goes, it'll throw away all the junk, and it'll focus on a good movement command.
Okay, now time for the parallel session. Thank you very much, Ken and Steve.